So we are moving to our next talk. So our next speaker is Dr. DebaJyoti Sahu. He is research fellow at the AiREX lab IISc. His work focuses on unsupervised learning, representation learning, and efficient AI deployment on edge and multi-sensor systems. He contributes to building trustworthy AI frameworks that operate in real-world conditions. So please welcome DebaJyoti Sahu.
Good morning, everyone. I am DebaJyoti Sahu, a research fellow from the AiREX lab at IISc Bangalore. It's a real pleasure to be here speaking in front of all of you with such a diverse community of researchers, academians, industries, and from people from startup. And thank you for showing up for today's session at CASML. Today, I want to share a piece of work that sits at the intersection of explainable AI, efficient deep learning, and edge deployment. The focus is simple. How do we take large deep networks that usually sit comfortably on GPUs, and make them run efficiently on small edge devices with tight memory and strict latency budgets? My hope is that by the end of this session, you will have a clear high-level understanding of why our method of compression works and how it fits broadly to the broader landscape of model compression. So let's begin. I would like to begin with a simple line. The future of AI isn't just about building bigger and smarter model. It's also about deploying them where they matter most. Over the last decade, AI has grown incredibly fast. We kept making models bigger, deeper, and smarter, and that progress has been amazing. Today, we have large language models with billions of parameters, models that can answer questions, write essays, and basically understand pictures, give us new generated pictures, and solve very good tasks with just a few short prompts. But there's a gap between these powerful models and the real world. The question now is, can these models run on small machines, basically the machines that make real-time decisions? So these machines that sit near the data centers are the small machines that actually need AI and need to perform the computation at the right moment. These are called as the edge devices. Basically, a few examples of these edge devices can be the computer inside a drone, a simple health monitor, a wearable health monitor that like an Apple Watch, a simple industrial sensor on a factory line, or we have seen some robot navigating in a warehouse and all. All of these devices work under tight limits. They have very little memory, low power, and must respond quickly. So the problem is clear with us. How do we make this deep neural network small and efficient enough to run on edge devices without damaging the intelligence they have learned? So now let's see how models today compress these methods and why these approaches often fall short. When we ask how do people compress models today, the common answer is basically we try to guess which parts of the models are matter less, and we simply remove them. Before we go deeper, let me explain what actually compression means in simple terms. So we know a neural network is basically a huge collection of weights and parameters, sometimes millions and sometimes billions, and these weights are what the model learns during training. So when we say we want to compress a model, what we do is basically we can do something like removing some of the weights, merging or sharing some similar weights, and basically we can also store some fewer weights overall during inference. When we reduce memory usage, we reduce loading time, and often we reduce the compute needed at inference. So compression is basically making model parameter fingerprint much smaller. Now, if we ask the question again, how do people compress model today? The answer still remains the same. We guess which parts matter less and we remove them. The simplest approach is something called magnitude pruning. You train a big model, look at its weights, sort them by size, and cut the smallest one. The hidden belief is, if the weights are smaller, it's probably not important. But this actually isn't true. Sometimes a neuron with small weights still plays a key role in the decision path, so removing it can harm the model. Then there are a few other family of methods that try to do it in a better, intelligent way. They use some important scoring methods like gradients or Taylor approximation. So instead of using normal weights, they basically change the loss or gradients and see and basically help to rank the weights. So in practice, this method sounds smarter, but they are usually unstable and noisy. So they change And this methods, this second set of methods usually change depending upon the training method that we use. So they can also depend upon the batch of data that we use, even the random seed that we set up, and basically will change from one evaluation to another and hence are quite unstable. So these methods have a common pattern that they show up. One thing, they make very local decisions. They look at one weight at a time inside one layer at a time. They don't really see how neurons across different layers might be working together, and most of these methods are still black box. We only see which parameters are removed. We don't really get a clear reason of why the parameters were removed or were considered safe to remove. These combinations of three things, local decisions, noisy signals, and little to less interpretability, is exactly where this method struggle. So a better set of methods have also emerged. Let me give you a small picture of three common directions. First one, explain and prune. So the idea is, instead of looking at weight size, we use the explanation score to see which neurons actually contributed to the prediction. So explanation tools that can be used, like LRP maps or GradCam heat maps, basically which helps us to see which parts of the networks are activated strongly for a given input. So neurons that consistently show low contribution across inputs are removed. It's a good shift from small weight being considered as unimportant to low contribution based on scores being considered as unimportant, but still it's done layer by layer. The second set of methods, clustering and pruning, these are kind of pattern-based pruning. Here the idea is to look for patterns or behaviors. So in one thing, in many trained networks, we will notice that several neurons behave almost the same way. They activate for the same kind of inputs, react to the same patterns, and produce very similar output features. These methods detect this similar behavior by these methods basically group this similar behavior, and basically by grouping them, what we can do is actually remove or merge these entire groups into one instead of looking at single weights one at a time. So we moved from considering weights as individual numbers to considering them as a group, as a functional patterns. But again, it is usually restricted one layer at a time, so it misses neurons across different layers that might share the same role. The third, people have also tried the existing pruning methods to be edge aware. Basically, they ask, how can we reduce the model size with the device constraints in mind? So what we can, so by keeping in mind by stuffs like memory footprint, the number of parameters that must be stored, and the amount of computation needed, people also have tried improving these methods for edge devices. But even here, even with all these improvements, these methods share the same limitations. They look inside each layer separately, as if layers do not talk to each other. They use local signals like per layer gradients or per layer clusters, which are usually noisy. Importantly, they miss the most important thing. They miss cross-layer redundancy, where two neurons in different layers might actually be doing quite similar jobs. And the decisions that they make are usually black box. They have little to less no interpretability. You see what was pruned, but you never get a clear explanation of why the behavior was considered unnecessary. Deep networks, as we know, don't operate layer by layer in isolation. So if two neurons, one early, one late, in different layers are doing nearly the same thing, layer-wise pruning will never catch that. So what we need is basically a wide lens. So to look at how each neuron behaves across many inputs and across the whole network, instead of looking at one layer at a time and one input at a time. So instead of asking which weights are smaller in this layer, we can ask a more global question. How does each neuron behave across many inputs across the whole network, and who is actually doing a unique work and who is just repeating someone else's job? This is where our framework begins. The key idea is, instead of relying on weight, size, or unstable gradients, we look at neuron relevance patterns and how much each neuron contributes across many inputs. We use layer-wise relevance propagation. This gives us a much more stable and meaningful sense of importance. The second gap we address is redundancy across layers. Two neurons, as I mentioned before, two neurons, one early and one late, may actually be doing a very similar job. So traditional methods never see this because they only look within one layer at a time. So we perform global clustering, grouping neurons that behave alike no matter where they are placed in the network. The final gap is converting the insight into real compression. So after clustering, we form layer-wise subgroups and replace many similar neurons with a single representatives whose weights are shared. So The three key the three key issues that were unstable importance signals, layer by layer decisions, and hidden cross-layer redundancy, we overcome this by using LRP-based behavior fingerprints, global clustering, and a structured weight sharing method. Now that we have seen the gaps in the existing method, let me show you the overall framework we use to compress the model. This slide gives a high-level picture of the 4 stages. I will explain each one of them properly in later slides. For now, consider this as a map of the entire journey. So stage 1 is basically the LRP-based analysis to find the behavior fingerprints. We start by running layer-wise relevance propagation, or LRP in short, on a trained model. LRP will help us to tell how much each neuron contributed to the model's output for different inputs. If we do this across many inputs, every neuron gets a long vector of relevance scores, basically that captures what it exactly does, not just what its weight look like. We will get a matrix of neurons and inputs here. Stage 2 is basically the global neuron clustering method. Next, the matrix that we got from stage 1, we cluster those neurons based on how similarly they behave. So if 2 neurons, even in different layers, respond in similar ways across inputs, we treat them as performing similar function role, and this is where we actually start capturing cross-layer redundancy. The third stage, basically subgroups and weight sharing. Inside each cluster, we form layer-wise subgroups so the shapes actually match, and from each subgroup, we pick one representative neuron to keep its parameter. All other neurons in the subgroup simply share the representative weights. A bit technical, so here's an easy way to think about it. Imagine a workplace in a big company. You might find people in different departments doing very similar work. But when you actually standardize a role, you do it within matching job format. For example, in HR, you might have several recruiters who screen resumes in almost the same way. You don't need 5 separate styles of doing the same screening of resumes. You may keep one strong relevance workflow and align the rest to do it similarly. That's exactly what we do with the neurons here. If we group neurons behaves almost identically across the inputs, we keep one representative and let the rest share its parameters. So we remove redundancy without breaking the structure. And the 4th stage is basically fine-tuning and inference. Finally, inference, the model runs just like the original one, but with far fewer distinct parameters to store. I will discuss this stage 4 in detail later. But let's walk through each stage, starting with the first stage, basically LRP, and how it helps us build the behavior fingerprints for all the neurons in a model. The first stage, that is basically the layer-wise relevance propagation. The idea behind LRP is quite simple. For any given input, we ask each neuron how much did you actually help in producing its output. LRP traces the prediction backward and distributes what we call relevance or credit, basically, or the responsibility that the neuron has for the final decision. Think of it like reviewing a group project. When the final report is submitted, you can go back and ask how much each team member contributed to the final result. LRP is doing exactly this for a neural network, going back layer by layer and figuring out who truly contributed what. One important property of LRP is that when it pushes relevance backwards through the layers, the amount stays the same, nothing extra is added, nothing is created. The entire relevance remains constant across layers. So if a neuron gets a high relevance score, we know it genuinely contributed to the final output, and if a neuron keeps getting low relevance across many inputs, we know it didn't play much of a role to the output. To mention one thing, we don't run LRP for just one input, we run it for many inputs. So each neuron ends up with a long sequence of relevance values. 2 neurons, which in earlier method might have different weight values, but two neurons earlier, which have different weight values, can also show identical behavior. When we collect this behavior for every neuron, we build a large relevance matrix where each row is basically one neuron, each column is basically one input, and each number or each n into m product is basically how relevant that neuron was for that input. This becomes the foundation for the next few stages that we do. One thing I want to mention, why is too much importance on the global view matters. Let's say a neuron in layer 2 and a neuron in layer 4 might consistently respond to the same patterns in the data. So if we only look within layers, if we only look within layer 2 and if we only look within layer 4, we may completely miss this redundancy. By keeping the relevance full dimensional and full and global, we can capture this phenomenon of neurons in layer 2 and neurons in layer 4 behaving similarly. The next method is basically the global clustering method. Here the goal is to find the groups of neurons that behave in similar ways. Every neuron has from stage 1, every neuron got a long relevance vector, basically description of how much it contributed across many different inputs. If two neurons have similar vectors, it means they react to the same kinds of patterns in the data, and if they live in different layers, they have different weights, values, or look unrelated in the unusual parameter space. The method that we use for clustering here is k-means, and we have also tried with various other clustering methods like agglomerative and GMMs. At the end of stage 2, what we get is every neuron belongs to a group, a cluster of neurons that are essentially playing the same functional role across all layers and are able to capture the cross-layer redundancy. Stage 3 is actually where the compression happens. By now, every neuron in the model belongs to a behavior-based cluster, but neurons from different layers have different input-output shapes, so they cannot directly share parameters. So the first thing we do here is create layer-wise subgroups. Inside each global cluster, we group together only the neurons that have compatible shapes. For example, neurons that accept the same input and produce the same output size, we will only form a subgroup of them. We don't form subgroup of different inputs and different output size. This will help us keep the original architecture intact, and nothing about the forward pass will change here. We only reorganize the parameter bank here. The second part is basically we pick a representative neuron. So once we have a smaller shaped matched subgroups, we need to pick one representative whose parameters will be kept. There are two simple methods that we used. One is a centroid-based method, and the second one is a medoid-based method. Centroid-based method is basically we average out the weights of all the neurons in the subgroup to create a synthetic representative, and the medoid-based is basically we pick the actual neuron whose weights are closest to the center of the subgroup in the cluster. And the third part, basically share its parameter within the subgroup. So after selecting the representative, all other neurons in that subgroup will share its parameter, and their individual weights are no longer stored. So the main thing is, instead of storing the full weight matrix of thousands of neurons, we only store a small set of representative parameters, and this is basically the main goal here. Since the number of clusters is much smaller than the number of actual neurons that are present in the model, this gives us a very large reduction in parameter count, and importantly, in networks architecture stay the same. Like in pruning, we don't cut or prune anything, we only store less parameters, and the forward pass also remains the same, only the stored parameters set becomes smaller. We are not removing anything or cutting anything, we are just removing repeated behavior in form of parameters. Okay, before we go deeper, let me quickly address a few points often that came up for me during my work here. First one is LRP architecture agnostic. Yes, LRP can run on MLPs, CNN resonates, and even transformers. As long as we can propagate relevance backward layer by layer, only the redistribution rules changes slightly depending upon the layer type. There are various LRP methods like alpha, beta, epsilon methods. Only the method changes, but it can be done for all types of architectures. Second, why use the full relevance vector instead of PCA or a smaller projection? Because by reducing the dimensionality, some of the features might get blur. Projection what it does is basically mixes feature, and we may lose cross-layer redundancy. We want to see the global actual dimensional dependence and not just layer-wise. Weak but consistent correlations between neurons, especially across layers, often vanish after projection. Since our goal is to look at the relations globally, we don't usually use the PCA method. So one important part, how do we pick the number of clusters, or how do we tune K as a hyperparameter? Starting, this is an important point. We use K in the beginning as a clustering hyperparameter. We use K first to get a range of values, basically a reasonable range. We can use methods like elbow method or a silhouette score. They don't usually give us the exact answer, but they tell us where to look. Basically, this gives us a range. Let's say a range from 120 to 150. Then we use K as a compression hyperparameter. Once we got a range, let's say from 120 to 150, we do a small sweep over that K range and see where accuracy actually accuracy is actually stable, where compression is high, and where both our target meets. Basically, to find a sweet spot. So this K value within this ranges of K is quite sensitive. When K increases, we will see in in the result section, the accuracy naturally improves. When K decreases, compression naturally improves. In the middle, there is always a clear sweet spot that we want to find. A few other questions like what metric tells us if clustering is good. We use normal clustering methods like silhouette square and dB index. But just to mention, the goal, but in a compression setting, the real metric is model accuracy. The goal is not to find good cluster. The goal is to find the K value that will help us get a better accuracy of a compressed model. The goal is not to get a good clustering, good compact clusters. Our rule is if accuracy is stable and metrics don't fluctuate too much, then clustering is good enough to move forward. We don't over optimize on the clustering metrics. What matters is how well that compressed model performs. This hyperparameters, few other hyperparameters that we tuned, as I mentioned, K for clustering, choice of the representatives like centroid or medoid, and small LRP rule settings like alpha, beta, or epsilon. Okay. The stage 4 or the final stage is basically where everything comes together and the compressed model actually runs. After stage 3, we remember every neuron has been mapped to a representative now. So how inference works. Instead of storing a full weight matrix for every neuron, each layer now stores a small parameter bank, one row per representative neuron. We also maintain a lookup map that tells each original neuron which each representative it should be. So during inference, the model simply looks up the correct representative row, performs the usual linear or convolutional operation, and continues forward exactly like the original network. It behaves like the original network, just with far fewer parameters to use. Fine-tuning is quite optional. If we want to squeeze out the last bit of accuracy, we only do that. The key point is we never unfreeze the whole model, so even fine-tuning remains memory efficient. Okay, so let me show how well this method works in practice, both in terms of accuracy and in terms of compression gains. We first tested it on a simple 10-layer fully connected neural network on the MNIST dataset. The uncompressed model has about 1.55 million parameters and achieves around 98.81 accuracy in its baseline as its baseline. Just to mention what I term as a parameter, the parameter is simply the learned weight in a convolutional or linear layer that we learn during training. As we know, more parameters means more memory usage and harder to run on a small device. So when I say 4 times compression, it means we reduce the number of stored parameters to 1/4. 8 times compression means we store 1/8 of the original parameters. So the plot on the right shows something very important. Each point corresponds to a different value of K, the number of clusters, and as K increases, we allow more representatives, so accuracy goes up, and as K decreases, compression increases. So what we see is a very smooth and predictable behavior. So the main takeaway from the curve on the right is accuracy recovers quickly, compression is tunable, and the curve is stable, and this is exactly what we want from a practical compression method. This slide, basically, we have tried to compare our method with the existing pruning-based methods. So for example, at 4 times compression, magnitude pruning drops to 98.10 accuracy, while our method stays up to 98.4. At 8 times compression, magnitude has a accuracy of 95.8, and ours still preserves around 96. Which is equally important in terms of inference speed. On Jetson AGX, latency drops from 5.1 at baseline to 4.34 at 4 times compression to 4.1 at 8 times compression. And on Raspberry Pi, we see a similar improvement, 20.38 baseline, 17.3 at 4 times compression, and 16.6 millisecond at 4 times compression. I will just quickly go through this on ResNet on CIFAR 10. Basically, ResNet, we tried it on a larger and more practical model. what you see in the plot is how the test accuracy evolves as we vary the number of global clusters K. The highest accuracy, 94.49, 94.9, basically occurs nearly at K equals to 90. Basically, instead of taking the entire neuron parameters, we can use only K equals to 290 parameters count during inference corresponding, and it will help us very close to the original model. Okay. Regarding its inference speed and comparison, magnitude pruning started with a 92.2% accuracy, and we have maintained a 93.27% accuracy. At 8 times compression, magnitude pruning drops to 90.2, while our method stays up to 90.45. And similarly, at Jetson AGX and Raspberry Pi, baseline is at 20.9, while at 16 times it drops to 18.2, and Raspberry Pi at 16 Raspberry Pi it still maintains 17.4 seconds. One point noting is the compressed models have consistently performed across very different set of hardwares. For example, starting from an RTX A6000 to a Raspberry Pi to a Jetson AGX, all have the same accuracy, just changes in the time duration. This means the model and the framework that we are using is actually platform agnostic. It basically write once and deploy anywhere kind of framework. So to wrap it up, we have seen LRP guides stable behavior level neuron profiles, and global clustering will help us reveal cross-layer redundancies. And for some of the few future directions that I want to pursue is basically extend this to transformers and attention layers. Thank you.
So thank you, Dev. Any questions?
Hi, I'm Dr. Sundar. At the higher level comparison, quantization methods have been widely used in industry.
Yes.
But you have chosen the pruning method for your research. So could you justify the idea behind this choice?
If you are mentioning quantization methods, we have also used some of the quantization methods on small edge devices, smaller edge devices than Jetson AGX, post quantization methods only. If you are asking why pruning methods as a research method, the goal was to see neural networks as a smaller compact model. So starting with pruning as the base methods, like how they cut the neurons instead of taking the entire neural architecture alone. We wanted to keep the architecture while doing something different. That's why we moved ahead, starting with pruning as a method.
But at the end, to improve the performance or reduce the efficiency, okay? So I think you should compare the best available quantization method with your pruning method so that it will be fully justified. Comparing among the pruning method may not be sufficient.
Okay.
Point number 2, the test level you choose the ResNet 18, right? But ResNet 50 has been widely used actually. So why did you choose ResNet 18 instead of ResNet 50?
We were gradually moving as we were increasing the architecture level. We started with a smaller 10 layer FCNN. We moved to a ResNet 9. We moved to a ResNet 18. We have also tried with VGG 16 and all. ResNet 50 we haven't mentioned. VGG also we haven't mentioned, but we have tried with VGGs also.
Yeah, an additional point. Yesterday, the students group has presented LoRa fine-tuning. So related to this concept, actually, I would suggest them to go for QLoRa. Right, okay. Quantized LoRa actually. Okay. That's it. Thank you.
Actually, the goal is fine-tuning should be as little as possible, because if you're fine-tuning, the goal of compression would be kind of not hold that much. So we do kind of fine-tuning, but it's kind of last layer stuff, like last layer bias or something. We don't want to look too much into LoRa and all those stuffs too much deep, but because we just want to show that it's just we keep the forward pass as similar as possible. We don't want to fine tune as much as it is. Even we are happy with few drop in accuracy, but we just want to keep fine tuning a bit far from our method.
Hello, can you hear me?
Yeah.
So did you try quantization aware training?
Yeah,
sort of thing,
quantization aware training. Yeah. We tried few quantization methods in the post inference method, like just decreasing the integers values. Quantization aware training we haven't tried.
And the layer fusion, I mean, typically after the model is trained, typically you do layer fusion, right?
Layer fusion in the as an inference during inference for yes. Basically ye method.
Yes. So didn't it improve the performance? I mean, like in terms of compression.
Are we considering that as a fine tuning method?
Not the fine-tuning method, basically for the compression of your model. So if you basically do layer fusion, you will have less number of parameters right now. So yeah. And how did your method basically compare with that layer fusion method? Which
The
typically
goal was to basically move away from pruning as a method. We saw pruning as a method. We wanted to do something different from that. These methods like last layer compression and last layer fusion and all, we haven't tried with that.
I see. Okay, thanks.
So one last question.
Hi, really nice presentation and great work. So I have a question regarding the correlation between relevance score and weights. So did you notice that with higher weights, the relevance score was also higher, or nothing of that sort?
Nothing of that sort. It might also happen that weights that are of different weights basically might have same relevance score based on the inputs, different inputs. So each row will be a neuron, and each each column will be a input data input basically, and even different neuron with different weights can have the same relevance scores. Thank you.
So thank you, Deb.